Loud. Okay, I think we had this slide last class period, right? Make sure you know the HR diagrams. You can reproduce it or you can identify things on the HR diagram. Just a quick, for the record, I'm continuing to review. I only have 2 more slides to review and then it's going to be off the cuff without pictures. But I will be reviewing. So when we look at these, what is a white dwarf? It's a dead star. It's a dead star. What keeps it from collapsing? Which seems kind of funny because what keeps the Earth from collapsing is a completely different thing. And that's what we would tend to think. Well, same thing. What keeps it from collapsing? Well, not enough mass. 1.4 solar masses would be enough mass to make it collapse. But what's keeping it from collapsing? It's an important concept. That's why I'm asking the question.
It's still some kind of fusion.
It's like the neutrons not being able to collapse on themselves, so they push each other out or something.
It's the right idea, but that's a neutron star. For the white dwarf, it's electrons instead of neutrons.
Oh, yeah.
Now, the white dwarf is primarily carbon, oxygen. The low mass white dwarfs might be primarily helium, but primarily carbon and oxygen atoms. But it's electron degeneracy, the fact that you cannot force electrons to occupy the same space, that keeps it from collapsing. And when you get to that Chandrasekhar limit of 1.4 solar masses, that's when you actually have enough mass to force electrons into the nuclei, in which case you have kablooey, a type 1a supernova, where it just blows up to smithereens. Doesn't become a black hole, doesn't become a star, it becomes just a big nebula. Okay, so white dwarfs, they're all roughly the same size. So if you look at that white dwarf line, that's roughly constant radius for the angle there. What's special about this main sequence? What's special, or what's going on in the star on the main sequence? You have hydrogen fusing into helium in the core of the star. That's what's going on in the main sequence. So the main sequence is where stars are in brightness or luminosity and temperature when they have stable hydrogen fusion in the core. And so what are these stars out here? What's going on with them?
They're beyond that. They finished fusing the hydrogens.
My brother's calling me to say happy birthday. Isn't it nice? Unfortunately, I'm in the lab. Go ahead.
I just lost my train of thought. They've finished up, like the shells have gone out, like the helium.
Okay. You have hydrogen fusion in the core has run out.
Yes.
And so the core starts collapsing. You have the hydrogen shell burning outward. And when this process happens, the star expands. And as it expands, for the 2 of you, we've talked about, expansion. The ideal gas law means cooling. So it's cooling, so it gets colder, which on this HR diagram means it moves to the right. It expands, which means it moves up and to the right. Radius increases going something like this. Temperature decreases going like this. So getting bigger and larger radius is moving out this direction, getting more luminous. And so in these stages out here, you could have a number of different things. And this is part of the off-the-cuff part of the lecture. We're going to talk about the birth, life, and death of stars, and this HR diagram is a great jumping off point for that, because normal life, 90% roughly of the life of the star is spent on that main sequence. Now, to stay in the same place in the main sequence, obviously just for linguistics you can answer. No, I had a student tell me once, I got an A in astronomy and I didn't learn anything. All I did was use linguistic analysis on the questions on the test. Good to know. It's not staying the same place. The sun is not at the center of the main sequence. It's not at the edge of the main sequence. Where would the sun be when it first reached stability on the main sequence? No recollection? Yeah. They start on the bottom left edge of the main sequence, and then through their lifetimes, they do something like this across that band. So the main sequence has a width to it because the stars aren't exactly the same throughout their lifetime of stability. Because you start off with more fuel in the core, and you end up with less fuel in the core. So that's going to change the dynamics, the efficiency of the burn. Or fusion, as you remember, that's what's really going on. So you have a width to the main sequence. That is the way that we determine the age of the sun to be about 5 billion years old and a full lifetime of about 10 billion years. Remember, we saw 10 billion one place, 11 billion in another. I know that's a difference of 10%, but it's still 10, 11. Between friends, we can handle that. You know, if we go out to eat, you give me $10 on an $11 bill, I probably won't be too angry. Although I am stingy, so don't try it. So that's the main sequence. That's the life of the star. 90% of its life, roughly. Now, how long does it take to get to the main sequence? Depends. Great answer. So what? Depends on the mass. Which ones are born faster? The bigger ones or the smaller ones? Big ones are born much faster. Bigger mass, everything happens faster. So the big ones are born faster, they live faster, they die faster. So a supermassive star, if you look up here, Spica, I believe it's pronounced Spica, maybe it's Spica. My mom would pronounce it, she might call it Spuka. It was very embarrassing when she came to visit me in graduate school. She kept asking people how to get to Spokane. Spokane. Anyway. I told her many times. And I also told her I knew how to get there. But no, she still had to ask people, how do we get to Spokane? So, Spica up here, assuming I pronounce it right, that's a very massive star. Because the higher you go on the left of the main sequence, the more mass you have. The more massive stars are burning hotter because it takes more outward push. Remember, you have the hydrostatic equilibrium. You have gravity pulling in, you have to push out harder because of more mass. Hence, you have to have a bigger explosion. So they're burning hotter, and because they have more mass, they're bigger. So bigger, hotter, brighter. Lifetime for something like Spica is going to be measured in millions of years, whereas the lifetime of our sun is measured in billions of years. And if you were to get way down here, Proxima Centauri, look at this. What type of star is Proxima Centauri? It's a what? Okay, red dwarf. I didn't hear what it said. It's right close to the cutoff to brown dwarfs. It's a tiny little star. And so its lifetime is going to be somewhere getting up to the, nearly trillions of years before it will die. I don't think it's trillions of years. I think it's hundreds of millions or hundreds of billions. But very long lifetime because low mass, it's just burning the fuel very slowly compared to large mass. Okay. So when stars are born, they're going to start, we mentioned on our review yesterday, in a cloud of gas. That cloud of gas, a molecular cloud. The ones that are thick and dense and have very cold temperatures like 10 kelvins. So the particles are moving very slowly. You get a shock wave, bring them close together, and they can collapse. Now, I was going through and did the homework solutions last week for lab. Was it last week for lab? And I did the entire homework. Was it 2 weeks? It was 2 weeks ago. I didn't notice when I was doing the entire homework that I had a typo in it. When I did it today, I was like, uh-oh. It said, super hot clouds, 106 kelvins. Or, yeah, it said ultra hot. Well, 106 kelvins is not ultra hot. It should have been 10 raised to the 6 or 1,000,000 kelvins. So I did the solution with both sets of numbers. I wish I would have noticed when I did the problem in lab. Okay, so that's not where it's in the 10 kelvins range, those molecular clouds. So it starts 10 kelvins way out here. So that's where a star is going to start its lifetime. Doesn't matter how big the star is, it's going to start way out there. And then you have a shock wave that comes, things start collapsing. As things come in, you start crunching, you compress, just the opposite of expansion. When you compress, the temperature goes up. So the temperature is going to go up, which means it's going to have to go to the left, and it's going to start emitting more radiation, so it's going to go up. So it's going to be going something like that. Not a star yet. It's a collapsing cloud, if you will. And you can't see anything. Now remember, we saw some cool pictures of the eggs in the Eagle Nebula, the evaporating gaseous globules, or whatever it was called. Kind of a made-up name for a developing star system where you have all this gas around the star. You don't see the star, because, well, it's not a star yet, the protostar, because of all the gas. But if you could, it would be giving off a lot of radiation, and then something special happens. And what happens? Boom, hydrogen fusion begins. So here, I'll put a big X. Boom, hydrogen fusion begins. Well, then it's a star. A star is born when hydrogen fusion begins. And when that happens, it's going to come down here to the main sequence. So it migrates to the main sequence. Something I did not talk about, I forgot completely talk about variable stars. That's what the next, I added 2 slides, and that's what the second of the 2 is variable stars. You have some variability that occurs as it's coming down to the main sequence. So you have a variable star that can occur there as it's coming to the main sequence, gets to the main sequence, and then it starts burning across as I have the yellow. So the blue is the birth from start to making the main sequence. 90% of its life is on the main sequence. For something like our sun, what's it going to do when it leaves the main sequence? It's going to have the shell of hydrogen, as Mira talked about. By the way, there are such a thing as Mira variables. They are, I believe, what I circled there, the forming stars that are going through instability as they join the main sequence. They have periods of getting brighter and dimmer that are on the order of a year. Just so you know.
I know there's a Mira A and Mira B star.
Which is probably where the Mira variable comes from.
Okay.
Just like you have the Cepheid variables and the R.R. Leary variables, named after Delta Cephei and R.R. Leary. Okay, so it's going to have a shell that grows out and it'll be a red giant. And then something cool is going to happen. That cool thing is it will suddenly have helium fusion occur in the core. When helium fusion occurs, depending on the mass of the star, you can have it occur 2 different ways. You can have it finally reach its high enough temperature and pressure that it slowly eases in. Or you could have it reach electron degeneracy before fusion of the helium begins. And if you reach that electron degeneracy, remember that same thing that holds up a white dwarf, then it can't compress anymore. And as pressure increases, instead of getting smaller, the temperature just goes up. And when it actually starts fusing, then the whole thing starts fusing at once instead of slowly beginning. So you have a big, huge explosion when it starts, and that's called the helium flash. And after that helium flash, you have stable helium burning, and I'm running out of colors here in my picture. Black will not do. That was a terrible, terrible choice. Yeah. So it comes back down, and it has a little stability out here. There's a second main sequence because you have stable hydrogen fusion going on in the core. Even though you have a shell of helium burning out at that point, when you reach stable hydrogen fusion in the core, you'll have a short second main sequence. It's not on the first main sequence. It's not called the main sequence. It's a second yellow giant main sequence. Then when it runs out of hydrogen or helium in the core, what's going to happen? Well, no, when it runs out of helium in the core, it's going to go back to a second giant stage. It's going to have a helium shell burning out. It's going to expand more, get cooler, go back into another giant stage. And then for our sun, we're right at the cusp. It may do something cool, it may not. That cool thing is called a planetary nebula. The sun is blowing off material. When it gets into death stages, it'll blow it off much quicker. So you have a lot of gas that's blown away. That's how you end up with an 8 solar mass star that's less than the Chandrasekhar limit when it dies. Because it blows off way more than half of its mass. So you have all this gas that's been blown off. When it dies, you have a collapse and a rebound that sends out a shock wave into that gas. And if you have enough gas, enough energy in the shock wave, that gas gets energized, the electrons get raised to higher energy levels, and they fall down. And what happens when the electrons fall to lower energy levels? They give off light. We call it a planetary nebula because the colors are similar to the colors you see on Uranus and Neptune. Has nothing whatsoever to do with planets. It has the same colors as Uranus and Neptune, hence the term planetary nebulae. Nebulae, plural, of course, of nebula. And then the sun is going to do its final thing. What's going on here? It's shrinking and cooling, and you're left down here with the white dwarf. So that's the life sequence for a sun-like star. Now let's take a smaller star. What if I have a star that's less than a quarter of the mass of the sun? What's different about that makes it die completely differently?
It can't go any further than helium, diffusing helium.
Okay, well, it does have that, but it also has complete convective mixing. Right? Our sun has in the outer atmosphere convection. Outer atmosphere, the final, 1/3-ish of the radius. I made that number up, but I think it's close, right? The inner 2/3 of the radius is the radiative zone, where basically the hydrogen atoms, or protons if you want to be more accurate, they're not really moving much. I mean, sure, they're swirling and whatnot, but they're not doing a lot of motion. And energy is being transmitted through radiation, like light. But that light goes this far and gets absorbed, and then re-emitted, absorbed, re-emitted, and the directions are random. So it takes like 100,000 to 1,000,000 years for energy to get out from the core to the end of the radiative zone. But then you have the convection zone, you have the the hydrogen, moving up, coming back down because hot stuff rises, cold stuff sinks. And so you have rather rapid transportation of the energy from that point. If you have a star that's less than a quarter solar mass, you're going to have complete convective mixing. You're going to have convection going from the core to the photosphere and back to the core. Well, in that case, when the core runs out of hydrogen, the star's out of hydrogen. And so you're not going to have the option of a shell of hydrogen burning out. It's just going to be done, which is what Merritt said, right? So small mass stars aren't going to go through the giant stages. They're just going to fade away, become white dwarfs. They're hydrogen or helium white dwarfs. If you get a bigger star, now our sun's right on the cusp, a little more massive, definitely have the planetary nebula. But if you get really big stars, then you're going to go through more exciting giant stages. Instead of just having the hydrogen shell and helium shells burning out, you'll have fusion of stuff up through producing iron. And so really massive stars will produce all of these elements with all of the shells burning out at once. And each successive one goes much faster than the one before. So essentially, by the time the hydrogen shell is done, all the others will be done too. They're just chasing it. And so those are the ones that are going to get really big and have exciting things. What's the cutoff for becoming a white dwarf? Okay, 1.4 at depth. But what about for a living star? Yeah, somewhere around 10 solar masses. 8 solar masses is when it starts to get more like silicon, magnesium in the mix. And up to 10 solar masses, that's about what they consider the maximum size for it to lose enough mass to be under the Chandrasekhar limit. Once again, you think about that. 10 solar masses down to under 1.4, right? It loses about 7/8 of its mass in the death stages. A lot of gas blown off. And what is that gas blown off primarily going to be? What element? Hydrogen, right? Because any question that you're asked, what's the primary element? If it's something that's not like in the atmosphere of a planet, it's hydrogen. Okay. So, what happens if you have more than 10 solar masses for the living star, so you end up with more than 1.4 solar masses at the death stage? It's going to have a supernova, a type 2 supernova, where you force the electrons into the nuclei at the death of the star, and you very rapidly reverse basically the entire fusion process. And you end up converting all of the protons that were there in the nucleus into neutrons. And electrons are absorbed in the process, so your electrons disappear, your protons disappear, and you just have a nucleus filled with neutrons. And that neutron thing is now really hard and really, really dense, as dense as the nucleus of an atom. And so when everything collapses down on that, the nucleus doesn't care. It just bounces off and you have a shock wave that goes flying out. And that shock wave then creates the massive supernova. If you have enough mass in a small enough region, instead of creating a neutron star, what do you create? A black hole. Right, so the black hole occurs if you have a high enough mass density. And, boy, I don't remember what the cutoff for that was. So I won't tell you that number since I don't remember it. So we have these different death stages. Now let's talk about about neutron stars. What's another name for a neutron star? Discovered by Jocelyn Bell. She called them LGMs as a joke.
Little green men.
Little green men. And what are these things that they called LGMs? They're what?
Pulsars.
Pulsars, yes. I thought I heard you say Martians.
What? I was guessing.
That's, of course, what the joke was. Okay, they were aliens of some sort. Pulsars. Pulsars are neutron stars. When Jocelyn Bell discovered them, when I was 1 year old or so, who knows how old I am today? What do you think?
Would it be grade if we studied a number higher
higher than what he's shooting at.
Probably, yes, probably. Guys are full of guesses. Out?
It's a.
You think like
Also,
50
oh,
or
that's
51? What math did you just?
You might as well just not come to the testimony.
Yeah, I did just say that she discovered them in didn't I say 1967?
It's math, man.
It's like you're 50 or 51?
52.
52.
I was
74.
I was thinking about
When I
I was
looked at
thinking
it,
like
and it said,
53.
like, I thought it was.
My wife thinks I'm 54 and she's 52. She's 53 and I just turned 52. Oh wait, you're not supposed to tell a person.
Yeah.
Woman's age, that's she somehow forgets that she's older than me.
I was going off of your Sierra Leone
Yeah, that's,
thing.
okay, so back to the topic. 1967, she discovered these LGM signals. Signals that were bursts of radio energy. And they were very reproducible. And looking at the bursts and then finding other ones, they were way too fast for it to be a star fluctuating. And way too fast for any star to be rotating. They would just fly apart. And even a white dwarf, if it was spinning that fast, it would fly apart. The only thing that could spin that fast and not fly apart would be a neutron star. And so that is the line of evidence, the reasoning that led them to say these pulsars must be neutron stars that are spinning really rapidly. Now think about it, why would a neutron star spin rapidly?
Because the mass is so packed with tight.
Yeah, you have general rotation. Remember the little example we saw with the Lycra, where he made the marbles go in both directions, and because on average you're going to have a little more in one direction than the other, ended up with them all going the same direction. So that's what we have for our star systems. You start with gas going in random directions, but on average you're going to have an average direction. On average you have an average direction. Oh, really sweet logic. And so you have things rotating, and then during the death, you have stuff shrink in, and it spins really fast, and it freezes the magnetic field. And so you have this thing spinning really fast with the frozen magnetic field. The magnetic field passes like this, and particles that pass through the magnetic field get excited and send off a beam of energy. And so that's what's creating the pulsar. So the pulsar has two beams shooting out as it rotates. And notice my beams are not parallel to the rotational axis. That's one of the funky things about these pulsars is the rotational axis is not the same as the magnetic field axis. If it was, you wouldn't have anything really exciting going on. Right? If the magnetic field is like this, it's going like this. The magnetic field is not going to be going through stuff and exciting and creating heat. So pulsars are neutron stars. If we see the pulse, we call it a pulsar. If we don't, we call it a neutron star. What's the temperature like on a neutron star? Very hot. What's the temperature like in a white dwarf? Also very hot. Because you have this thing contract, and when it contracts, it's hot. And you know what? It was already hot. Stars are hot to begin with. You have it contract, it gets really hot. So white dwarfs are really hot, but they're small, so they don't give off much light because luminosity is proportional to radius squared times temperature to the fourth power. Neutron stars are much, much smaller than white dwarfs. White dwarfs are, roughly Earth size. Neutron stars are roughly Lincoln City size. It doesn't matter how hot it is, if it's that small, it can't give off light comparable to a normal star. So neutron stars don't give off much light. Hence, they're going to remain hot for a very long amount of time. But they do give off energy because of those beams in rotation. That's rotational energy. That's not thermal energy. That's energy they have because of their motion. So they're slowly going to lose energy in their motion, so that makes them slow down. because of the energy that's coming out in the pulsars, the beams. So, generally speaking, the rotation rate should be dropping for a pulsar. But every now and then you'll have them do things like, and speed up. What would cause them to speed up like that? Somebody answered it correctly when I asked it in class the other day. Those little glitches, as it called them in the graph. Come on, I think it was you that answered it before. I don't know. What would make it suddenly spin faster? When I have a figure skater spinning, what makes her or him spin faster? Bringing their arms in. So to suddenly spin faster, the conclusion is it must be shrinking a little bit. And that results in it spinning faster. Now, the very fastest spinning neutron stars are old. Match that with what I just said about they slow down over time. How could the fastest spinning ones be old if they slow down over time? Piece of information. They're found with companion stars that are giving off mass.
So are they like getting bigger?
Mass from the companion is coming over, and as that mass from the companion comes over, it makes it speed up as it falls in. And so it spins them up. So the very fastest ones have companion stars that are dying. Okay, that leads us to black holes. Why is a black hole black?
Because it's too gravitational versus too much for light.
Okay, first explanation, the gravitational force makes it so that the escape velocity is faster than the speed of light. So not even light can escape. That's a Newtonian way of answering. Now we have a relativistic way of answering. What's the relativistic way of answering? When you have a massive object, according to Einstein, that warps the fabric of space and time. I did say continuum this time. I loved his joke about lending a rip in the space and time. So, mass warps the space-time continuum. I can't help myself. If you get enough mass, you actually warp it so you form a bubble. So space is warped into a bubble and there's no way out. There's no path out. It's not simply a matter of it doesn't have enough energy, it's that there is no path out. Because the space-time has closed on itself. And so that's another explanation for a black hole. That's what we believe to be a more accurate explanation for the black hole. So how do you get a black hole? You have to have enough mass in a small enough region to warp the space-time into that bubble. And then we have the question, this was a homework question that's due tomorrow, huh? What would happen if you fell into a black hole? You die at the end. Alex's answer is very short, to the point.
You get stretched out.
You get stretched, what else happens? You get hot. You get what?
Like I said, you get warped.
You're warped. How does your Apple Watch function? Assuming somehow you're magically alive and your Apple Watch still works. If you're looking at it, what does it say? I muted it. I was smart. Your watch, according to you, is going to just keep running like normal. My watch says happy birthday. Your watch just keeps running like normal, according to you, because you are in the same space-time as your watch. And so you just see your watch running like normal, you see yourself falling in, and actually you're inside a black hole, doing only God knows what. We don't know what it's like inside a black hole. My little favorite pet theory that other people have taken as their own, but I came up with it on my own, is that maybe we're inside a black hole. Maybe our entire universe is inside a black hole.
How's that work?
Okay, how's that work? Tell me what you know about our universe.
It's very big.
It's very big. Okay, that's a good start. Up until, 100 years or so ago, it was believed our universe was pretty much static. And then, as we'll see coming up in the next weeks, Edwin Hubble is the one who gets credit for observing that everything is moving away from us. Now, the interpretation of everything moving away is not the same as it was back in the day. Right? We used to believe that the Earth was the center of everything because of observation. Now we say everything's moving away from us because everything is expanding. If everything's expanding, it doesn't matter where you are, you're going to see everything move away from you. And in fact, the understanding we have of the universe is that the universe it goes on forever, and it's uniform and constantly expanding. And it gets really confusing when you say it goes on forever and it's constantly expanding, because you tend to think there should be an edge. And if there's an edge, there should be a center. But the scientific belief is there is no edge, there is no center. It's expanding, so space is expanding between things. Space is expanding. The things aren't moving, space itself. Cool stuff. Well, what has been discovered in the last, 30 or so years, maybe less than that, but I think 30 is pretty reasonable, is that the rate of expansion now is faster than it used to be. We're expanding faster, which means energy is coming into the universe. We have rules. One of them is the first law of thermodynamics, says energy can't be created or destroyed. And so we have dark energy, an unknown source of energy that's making us expand. How much of the universe is dark energy? I think they believe it's something like 75%. Somewhere in the ballpark of 75% is dark energy. And then maybe 20% or so is dark matter, stuff with gravity that we can't find. And about 4% of the known universe is matter, the stuff we know about. Everything we've been talking about astronomy, everything we know about, scientists believe is only 4% of the universe. There's all this other stuff we don't know about. Well, I'm talking about my pet theory here. We know that the universe, from all measurements, is expanding. The rate of expansion is accelerating, which means that energy has to be coming in. Now, if you look at a black hole has an accretion disk, and when stuff comes in, of course, you see eruptions coming from the poles of the black hole because magnetic fields redirecting stuff. But what goes on inside? All we can say for sure is there's now more mass inside the black hole, which means there's more energy inside the black hole. If you were inside the black hole, you would see energy increasing. So that would at least explain what dark energy is. It's the stuff falling into our black hole. But then there's other lines that also work. We have scaling in astronomy. We have things like our planetary system with the moon orbiting around the Earth. Moon orbiting around the Earth. Then we have the planets orbiting around the sun. Basically the same idea, just a bigger size. And then we have clusters of stars where everything's going around, a massive black hole in the center maybe. And then we have galaxies where everything's going around a massive black hole in the center. And we have clusters of galaxies. We just have scaling, the same type of thing, bigger and bigger and bigger. And so I'm thinking we could just have another scale, and there could be, we are a black hole in a bigger universe. Our universe is a black hole in a bigger universe. It makes sense. It's not some kind of crazy theological argument that would violate my Christian beliefs in any way. I've read at least one article of somebody who suggested a similar idea, except for what he said is, we're not inside a black hole. We are living on the Schwarzschild radius, if you will, the event horizon of a black hole. Our entire universe is in the event horizon of a black hole. Because you have a drop in dimensionality. If it was a 4-dimensional space, then you'd have a 3-dimensional space for the surface of the black hole. Very interesting, right? Now, that's not going to be on the test. But, I'm sorry. I probably should have stuck with what's on the test because you guys are worried about that, right? Alice's brain hurts, so, yeah. I was trying to relieve the stress. We've been talking about the life and death of stars and black holes. Black holes have that Schwarzschild radius that we calculated based on where the escape velocity is equal to the speed of light. That's a naive view of a black hole. It's a view of a black hole that is non-relativistic and not rotating. That's as far as we're going to go for this class. We talked about what happens if you fall in. You're going to see time running normally. You're just going to see, fell in. But if somebody outside is watching, as you get closer to the event horizon, the surface of the black hole at the Schwarzschild radius from the center, you're going to have time dilation kick in. So they're going to look at you and say, wow, everything is slowing down for Richard. You know, his watch is running super slow. He's breathing about once every year. You know, everything's just slowing down. And they would see you getting asymptotically closer and closer to falling in and never actually falling in because of the difference in how time flows. Which is pretty incredible, right? Pretty mind-boggling. That's one of your homework questions. Read your textbook to make sure you understand it. Black holes. How do we know black holes exist? If by definition you can't see them.
Just see like black place in there.
You see stuff around them. Because using Kepler's third law, we can, just like with a binary system, you can calculate what the mass of the binary system is by calculating the period of the orbit, right? That's actually how we get the first order of dark matter, by calculating the rotational rate of stars and galaxies. We find that there's a lot of mass we can't discover based on the rotational rate of the stars and galaxies. So using that same physics, looking at black holes, like at the center of the Milky Way galaxy, where in the sky is the center of the Milky Way galaxy? Toward which constellation?
The cup.
Teapot, which is an Archer, Sagittarius, yeah. So there is I think it's 3 million solar mass, I think that's enough, 3-4 million solar mass black hole there. I think I said 300, 400 in class before, but it's 3-4 million for sure. But that's a really big black hole. How do they know? By clocking the period of things going around it. They can determine there's this much mass there. It's this small a radius. You can't get that much mass in this small a radius unless you have a black hole. That's really strong observational evidence for a black hole.
Wait, but didn't you say stuff moves slower if it's going around it?
If it gets close, yes, because the time flow changes. And we can actually take that into account as well. If you get far enough away, it's not going to be a significant factor. Okay, I am going to move on now. Thing I didn't talk about. I won't put it on the test because it's not fair to pop it on you the night before the exam. But this is something that's important for us to talk about. So we talked about distance calibrations. We started with, we can measure the distance to the sun and other things in the solar system with radar. We could shoot electromagnetic waves out, measure the time for them to bounce back, and then just using the speed of light, we can calculate the distance. Not so hard. But that only works for things in the solar system. We can't do that for things farther away. We just, take the next closest thing, Proxima Centauri, 4.3 light years away. So you send out your radar signal and you wait 8.6 years for it to return. How strong is it going to be? It's not going to be strong enough for us to measure. So we can't use it for those things. So we have to go to something else. The next step is using triangulation with the process we call parallax. You measure the change in apparent angle from looking at a star depending on the season. This was first actually discovered in like 1838. It was something that scientists, I'll use the term loosely, back before Christ was born, knew should occur, but they didn't observe it. One of your homework questions, I don't think it's from this homework, I think it's from a previous one, is why not? Why didn't they observe it?
Technology, basically.
Because the angles for the parallax are too small for them to measure. Yeah, it was from 2 assignments ago because it's one that I did in that homework in lab. So now we can measure parallax. The Gaia satellite is out there, and they believe that it's going to be able to find parallax for lots and lots more stars. I think it's somewhere on the order of 200,000 stars right now. No, maybe it's 2,000. That we can calculate parallax for. Let's go with less than 1 million, and I'll be correct. So it's not that many stars we can calculate the parallax for, but that is a distance measurement. It's a pretty strong measurement, right? We make an angle measurement. If we're accurate with the angle measurement, the geometry is set. We're going to be accurate with the distance. So I have a lot of faith in the parallax method. I have a lot of faith in the radar method. If we go beyond there, we need to have faith in the further ones as well. Right? If we have calculations of how far a star is, we need to have some faith in it. So the next method I have up there is using standard candles, things of known brightness, known luminosity. We measure the brightness, you measure the brightness and compare it to the known luminosity, and using the equation that relates absolute visual magnitude to apparent visual magnitude, you can calculate the distance. So what are our standard candles? One that I've mentioned repeatedly, and the only one that I've mentioned repeatedly, is type 1a supernovae. Type 1a supernova, it's a white dwarf. Its mass is the Chandrasekhar limit of 1.4 solar masses. Pretty much the same material, the same mass, it's going to be the same thing. So type 1a supernovae are almost always exactly the same luminosity. So if you observe one, you measure its apparent visual magnitude. You compare its apparent visual magnitude with its known absolute visual magnitude, and you calculate the distance. So that's a standard candle. But there's other standard candles that are very important. I mentioned Harlow Shapley observing globular clusters and seeing that there were a lot of globular clusters in the region of Sagittarius. And so he said the center of the Milky Way galaxy must be over there because that's the only thing that could explain why we would have a cluster of clusters. Well, he then used Cepheid variables to calculate the distance. Now, Cepheid variables are named after Delta Cephei, Alpha, Beta, Gamma, Delta, the fourth brightest star in the constellation Cepheus. So, what's special about these Cepheid variables? They are stars that get brighter and dimmer. They're in the death stages here. Actually, maybe Mira variable is the death stage 2 for a star the sun's size. I have to look it up again. Anyway, these Cepheid variables, you can just measure the period, the time between getting bright and getting bright again, and that will tell you the luminosity. If you look at the graph behind me, it has on there the line that's going up and to your right is Cepheid variables. Now there's actually 2 lines that you can't tell are 2 lines in there. There's type 1 and type 2 Cepheid variables. So they actually, by looking at the spectra, they can determine if it's type 1 or a type 2, and that helps them to further pinpoint what the luminosity is. So you find a variable star. If it is the right type of variable, you look at its period and you calculate exactly what its luminosity is. So that's considered a standard candle. You can determine its luminosity independent of anything else. And then you measure its apparent visual magnitude. You know its absolute visual magnitude, its apparent visual magnitude, boom. You can calculate the distance. Now there's another type on this graph that has much shorter periods. They're the R-Leary variables. And those R-Leary variables, you notice the period is less than a day. Very short periods. And they all have very similar luminosities. So you find an R-Leary variable, and you really don't need to determine what the period is. You just say, oh, it's an R-Leary variable. Its luminosity is right here. And once again, you can calculate the distance. So that's a little more tenuous of a measurement for distance because it's relying on a proxy for bright or for luminosity. You don't know exactly the luminosity. You believe that the period tells you the luminosity. And then you have further issues like interstellar reddening. Interstellar reddening is going to change the brightness as well. So, of course, scientists will take that into account. They don't say, oh, la-di-da, we'll just ignore it. They actually do account for how much interstellar reddening do we expect from the distance we calculated and refined. So those variable stars are super important. What makes a star variable? It's really interesting. You have, of course, radiation coming out from the star, and when you're in the right stage of death, the atmosphere will be thick enough that it absorbs the radiation. As it absorbs the radiation, it gets hot. When it gets hot, it expands. And when it expands, it gives off more light. But then when it expands, it becomes transparent and the radiation goes out. And so it stops heating. If it stops heating, it cools down. If it cools down, it contracts. And then when it contracts, of course, then it's thicker, it absorbs, and so it's going through this cycle of getting bigger and smaller. And so we can understand the process that makes these variable stars. My last slide. Really? Nathan said, can you help me? And you know what I do when my son says, can you help me? I drop everything, apparently. Really dropped everything. What are the three types of nebulae? Dark, emission, reflection. What is your geometry for viewing a dark nebula? It's actually not a special geometry question. You're viewing something that is really thick, so light doesn't get through it. So that's molecular clouds, the cold clouds, are the ones that are going to give us those dark nebulae. What about a reflection nebula?
The sky.
Its color is the same reason the sky is blue. You have a star that's close enough, or maybe you're looking through the cloud, it's close enough to have significant scattering, but not close enough for the radiation of the star to excite the gas and make it give off light. If you're close enough to excite the gas and give off light, what are you going to have? An emission nebula. Right, so emission nebulae, scattering nebulae, it depends on how close it is to a star, fundamentally. And if you're looking through it, you'll see more reflection time. Those are our three types of nebulae. I think I've covered everything in the last 4 chapters here. But I didn't have slides for them, so I said I think. Are you feeling better prepared? Nope. Are you feeling more confused? Oh, good. If you said yes, then I was going to be a little disappointed. All right. It's cold out there. If you want to go out and observe the sky, I am totally game. It's your time, you paid for it. But if you don't want to go out, we've spent enough time with our astronomy tonight, you can go.
So you're saying we don't have to go out to the dam to...
That's what I'm saying. I'm saying you may if you like. If you like, I will be there. telling me though, I am not going to go out there and stand out there for half an hour like, where are these people? Getting cold, colder.
I have 5 tests tomorrow. There's no.
5?
Yes.
In 3 classes? Obviously, he's not taking 3 classes.
I haven't shown me tested.
He has a strong test to study for.
That's one of them.
Wait, so if we don't take it tonight, at least go out there, how many more times do we have to take it? What if it's cloudy? What happens?
If it's cloudy both times, then the second time we're going to take it on paper. And doing it on paper is harder. And so I give you an out. If there's good weather after that, like any time before the final, call me, we can go out. Right? Because it's going to be easier to do it looking at the stars than it will be doing on paper.
If you provide
What does doing it on paper involve?
Okay, I better have these on Moodle. I better. There are samples of the actual. It's exactly the paper you would have, except for it's a different season. Hence, it's not going to be the positions for the stars that you're going to have, just so you can't memorize and just say, okay, well, there it is. I memorized this. And so you'll have a paper with a bunch of dots on it. Bigger dots represent brighter stars, smaller dots, fainter stars.
Wait, so is it gonna be like the
I'm just going to pull it up.
panoramic view of the sky or something?
No one asked you. I like as long as you know where looking at the constellations and stars are on a map, then it's kind of almost easier to do it on a paper.
I can't say much. I already texted me last week, so.
I'm not advocating one way or the other. I'm just really tired right now.
I think this is it. What? Microsoft Word? Well, it's clearly not it if it's a Microsoft Word document. Yeah, we don't want anything dangerous.
Thank you.
Okay, so no, this isn't going to help us. I have it here, though. I'm going to stop the recording.